Okay. So I'm very happy today to introduce Dr. Matteo Baggioli to give today's quantum fluids and isolation seminar. So Dr. Baggioli got his Bachelor of Physics at University of Genova in 2009, his Master's also from University of Genova in Italy from 2012. In 2016, he got his PhD in physics from Universitat Autónoma de Barcelona in Spain. And it would, in between October 2015 and on January 2018, he was visiting a PhD position at the University of Illinois at the Institute of Condensed Matter Theory. From 2016 to 2018, he was a postdoc at the Crete Center for Theoretical Physics and the Crete Center for Quantum Complexity and Nanotechnology in Crete. And from 2018 to 2020, he was the Severo Ochoa postdoc fellow at the Institute for Theoretical Physics at the IFT CSIC UAM in Madrid, Spain. He's been awarded the PIF grant in February 2013-2017, and his postdoc was funded by the ERC Advanced Grant September 16th, 2016-2018. And today he'll be talking about hydrodynamics to viscoelasticity and holography and beyond. So please help me in welcoming Dr. Matteo Baggioli.
Okay, so welcome everyone. So first of all, let me see if this works. Okay, so first of all, let me thanks the organizer, Joshua, and to put all this event together. I think it's very helpful for all of us, not only from the physics perspective, but also for the mental health during this quarantine. And let me thanks all the collaborators around the world that put a lot of effort to basically finish what you will see right now. So today, I want to tell you some stories about phases of matter, solid and liquid, and I will do that from different perspectives. So I will start discussing it from a more condensed matter perspective, and then I will turn by the hand to see how holography can, if it can, help in understanding better these phases of matter, especially in some exotic contexts. So now the main topic that I will address is basically the following. So imagine that your child during this quarantine came to you and asked you help or some homework at school. And the homework is pretty simple, at least it looks pretty simple. It's just this kind of chart that you see here, and you have to basically cut out some picture and basically classify them in these squares. And so this looks naively, at least at first sight, a very stupid exercise, kind of something like that. And especially in the context of fluids and solid, the difference looks very, let's say, concrete and very clear to everybody of us. But actually, if we start thinking more deeply, this is not the case. So let me start from some real basics about solid and fluids to just start from a common ground. So solids are basically defined, at least usually, as materials that support propagating transverse shear waves, which are nothing else than transverse phonons. So the reason why these excitations are in the system is definitely linked to the spontaneous symmetry breaking of translations. And these excitations are nothing else than the Goldstone boson that appears because of these space-time symmetries are broken. And of course, depending on how many direction or how many dimensions you have different type of dispersion relations, and you have different types of mode, longitudinal, transverse, etc. But the most important thing that differentiate liquids and fluid, at least this is what they tell you every time, is that solid have propagated transverse shear wave and fluid do not. And this propagating transverse shear wave, at least the speed of these waves, is related to the properties of elasticity, so to the rigidity of the material itself. Now, fluids. Now, if you go to fluids and we focus ourselves to the transverse sector, so all the excitation which basically propagate transverse to the, let's say, a select momentum, what we find is something very different from solid and is basically diffusion, shear diffusion. So this is linked to the conservation of the momentum in the system, and is deeply linked to the concept of viscosity and dissipation. So how can we understand this shear diffusion? Well, we can start immediately from some continuity equation. So let's imagine you have a current in the system. In this case, the current is actually the momentum current, but in more complicated setup can be some charge current or whatever mass current that you have in the system. And let's start from the continuity equation. So the continuity equation is just a statement that follows from symmetries. And then let's add basically the constitutive relation for this current, which is nothing else than the fixed law that comes, if you want, from microscopic Brownian motion or diffusive dynamics of particles. And what you get is exactly a mode that is diffusive. So this means that it's purely imaginary and it goes like k squared. So one typical example of these modes, this diffusive mode, is what appear in relativistic hydrodynamics, where this diffusion constant is directly linked to the viscosity, and it has a meaning, a deep meaning related to this eta over S ratio that we'll discuss briefly after. So at this point, it looks very, very clear that a solid and the fluids are actually pretty different. Nevertheless, I want to ask the question, are really fluids and solids different, and in which respect are different? So it's well known, and it's basically due to the work of a Russian physicist called Frenkel, and in this beautiful book that he wrote, Kinetic Theory of Liquids, that if you go to frequency, which are high, very high, actually higher than what is called the Frenkel frequency, which is given in terms of the inverse of a relaxation time that I will define in a moment, fluids actually are not very different from solids, in the sense that above this frequency, fluids support transverse propagating wave as fluids do. And this is tested experimentally. So for example, here you can see a scattering experiment. I think this is neutron scattering experiment. And you can see this is just in water, and you can see the appearance of both longitudinal and transverse wave at high frequency. Now, if you ask an experimental, your experimental friend, what is the difference between a fluid and a solid? Well, the first thing that he will propose to you is this kind of experiment. So it's a kind of shear strain experiment, which is done in the following way. So we take two plates and we put our, let's say, material, let's say your honey or your toothpaste in the middle, and we start applying from one side a strain deformation. And for simplicity, I will assume that this strain deformation is actually periodic. And then what we're gonna do, we're gonna measure from the other side what is the stress that this strain deformation produces along basically the material. So now if you do this simple exercise with an elastic solid, what you discover is that the stress signal and the strain signal are completely in phase. And they differ from each other just from a constant, which basically determines how rigid is the system that you're probing. Now, if you do the same experiment in a viscous fluid, in a perfect viscous fluid, you will discover that the stress that you obtain is actually completely out of phase with respect of the strain. And there is a pi-half angle of difference. Of course, if you put inside your apparatus a generic materials, the situation will be somehow in the middle between the two, and this is what we call a viscoelastic material. So the angle, the phase, will be between 0 and pi-half. The more close to 0, the more solid the system, the more close to pi-half, the more dissipative the system. So the reason of this phase is simply that the viscosity induces dissipation and therefore a delay in the response. Now, of course, you can formalize this much better than these figures, and you can just do some easy mathematics. And if you define like the signal in terms of, let's say, a cosine, like an oscillatory function with a certain angle that is exactly this angle, this phase between the two, then what people in rheology, which is exactly the field where people study the deformations and the flows of materials, are used to define what is called the complex modulus. So the complex modulus is basically in the frequency domain, it's just basically the proportionality between the stress and the strain. So this has an imaginary part, which we call G second, and a real part, which we call G prime. So from more, let's say, particle perspective or field theory perspective, this object here is nothing else than the Green function associated to basically the linear response. Now, what happens? So the real part of this object is what encode like the static and in-phase response, which is not dissipative, while the imaginary part encodes the dissipative response and is out of phase. So if you compute basically the frequency dependence of this object in a solid and in the fluid, you will get a very different result. But this is what you will get in a solid, where basically the real part is much larger than the imaginary part and it's approximately constant. And you can see that it goes almost all the way down to zero frequency, meaning that there is a zero response, a zero frequency response, which is exactly the static response given by rigidity. On a fluid, the situation is very different. And you can see here, for example, a cartoon. And basically, you can see, for example, that both the curves are going kind of to zero at zero frequency. This means that there is no static rigid response, no static elastic response. And the imaginary part starts always linear, and the coefficient which set this is what we call usually the shear viscosity. Now, why I'm telling you all of this? Well, because some time ago, actually a few years ago, there was an experiment by Laurence Noiret group in Paris that found something of this kind. So what you see here is they did exactly this kind of experiment. And what you see is that the shear strain, the shear stress are completely in phase, and the real part of the response goes all the way down to zero frequency, and it's much larger than the imaginary part. And now we can just play a stupid TV quiz and ask ourselves, well, accordingly to what we said before, what is this material, right? Everybody at this point will say, well, this is a solid, there is no question. Well, the problem is that actually this material where this experiment was performed was water. And so the paper that you can find at this link claims that here they have an evidence that liquid can support propagating shear waves, and notice also at low frequency, because this G prime goes all the way down to zero frequency. So now they are claiming that liquids behave like solid also at low frequency. Now, one thing which is very relevant here, and you have to focus your attention on, is this kind of data here. So this data is basically the separation between the two plates. So this means here, this distance is very small. This means that they are probing this response at very small scales. And this is crucial for our theoretical understanding. So our theoretical understanding, it's the following, and it's summarized in one review that we wrote this year. So the idea that goes back to Maxwell and Frenkel is that the equation that usually, let's say, encode and describe the propagating waves is not simply omega square equal v square k square, where v is the velocities of the shear sound, so they're linked to the elasticity, but there is another term which enters with a relaxation time, which we will call Maxwell-Frenkel relaxation time. Now, forget for a second where this equation comes from, and I can tell you in a while, but if we assume this equation is true, what you will get is a solution that looks like this. And why this solution is very interesting. So let's analyze this solution. So when momentum is mole, we can just expand in perturbative series this solution, and we find out that there is no real solution, just because this square root is, the thing inside the square root is negative. And what we find out is below this momentum that I will call K gap, basically the physics of this equation is very similar to the physics of liquid. So you will have only one diffusive mode with a certain imaginary part and nothing else, nothing in the real part. So there's nothing propagating. But then the curious thing is that at a certain point, at a certain momentum, something appears. And you see here, there is a propagating mode that emerges at a certain momentum, and it propagates. So it propagates with a certain speed, with asymptotically, it's given by this V. And this mode is coming from basically the collision between a diffusive mode and the non-hydrodynamic mode that comes up, they collide, and they produce this mode. Okay, so what this means? This means that if you are probing the system at very large K, or at least K, let's say, larger than this K gap, you will see a propagating shear wave even at small frequency. So you can go close here, for example, and even if you are at very low frequency but a large momentum, you will see basically this propagating shear wave. So what is the physics? So the first physics that you have to take in account that was proposed by those people is this tau, this relaxation time. So this relaxation time is linked to the idea that we have in describing liquids, which is basically the following. So liquids, you have to understand them as a bunch of molecules, or let's say of particles that are confined, yes, in a potential. So they have some kind of potential, but this potential is not so strong. And especially at finite temperature, there is a probability that these particles basically jump between one potential and the other. So if this was a solid, basically this particle will only vibrate around the minimum position, and they will not have any chance of actually diffusing around. But in a liquid, basically this particle can jump, and this tau, this relaxation time here, is basically the average time of rearrangements of this particle inside the liquid. More, if we assume, for example, Maxwell theory of viscoelasticity, this time here is nothing else than the ratio between the viscosity, the shear viscosity, and the shear model. Okay, so basically when the shear viscosity is 0, this time is infinite in the sense that they will never basically jump around. Now, another way to see this is that if you look at a liquid, and if you look at distances which are smaller than c tau, where basically c is the speed, sorry for the change of notation, and tau is still this time, then at these distances, a propagating wave, a shear wave can propagate. So basically, if you look small enough and you coarse grain the liquid, you will see that the difference with a solid is basically absent. It behaves exactly like a solid, but the difference is that the shear wave has a finite propagation length. And this finite propagation length is set exactly by this tau. So this was confirmed by some of my collaborators in a PRL paper doing molecular dynamic simulations. So here you can see the results. So what they do is basically they simulate in a big computer like a bunch of particles, assuming certain potential, most likely a Lennard-Jones potential. And what they see is they compute basically the current two-point functions. And from there, from the peak moving in the current two-point functions, they can basically derive the dispersion relations. So here you can see the dispersion relation increasing the temperature, and you can see this K gap moving. So here you can see exactly where this propagating mode starts to open. And you can see that basically the higher the temperature, the more this gap is moved to very, very small distances. Okay, so this is consistent with the fact that tau decreases when the temperature increases. Now, very recently, only 3 days ago, the same group put out like an experiment where they do inelastic neutron scattering on gallium. And these are the results. And there is at least preliminary evidence that they see exactly this kind of behavior in gallium. From our side, from the theory side, we find, let's say, an interesting question to find out which kind of field theory or which kind of, let's say, theoretical construction can give rise to this kind of equations, which sometimes is known also as telegraph equations. So in the review, we wrote a lot of actually physical systems where this kind of behavior happen. And here recently, we just focused on a toy model, or on a simple toy model of field theory with the scalars to try to understand. And what we find out is that in order to have this kind of behavior, you need to consider a kind of weird field theory, which is non-Hermitian, but is PT invariant. So you have to set basically an interaction terms here, which plays the role of basically the viscosity, and introduce dissipations in the system. Now, this kind of field theory is clearly non-Hermitian, so it has to be taken a bit cautiously. But thanks to the work that it was done in the last year, making sense of this kind of field theory, we are able still to treat it. So this field theory has a unitary evolution, it has a Hamiltonian, which makes sense, etc., etc. And the picture behind this, this field theory is that basically you have to think as the liquid as a kind of basically two systems. And these two systems are basically related to each other by gain and loss. And the phonons, if you like, these waves are moving around, they are colliding, and every time they collide, there is one phonon that basically gain energy and one which lose. And in a way that the full system is still, let's say, still conserve these things. And what we find out, what we play around is that we computed basically the two-point function, if you want the correlator or the propagator of the scalar, and we find out basically that there is exactly this kind of transition. When we go at very large distances, we don't see any oscillations, any minima. But then when we go at small distances, basically this kind of theory predicts that the appearance of oscillations which are related basically to the solidity, to the solid properties of the system. Now, so the final answer that I want to kind of propose is that fluid and solids are only quantitatively different, but not qualitatively. So the statement that in fluids there are no propagating shear waves is not totally correct unless you specify in which time scales and in which length scales you are actually describing your system. And to make an analogy, there is also another, let's say, place where something similar happened for completely different reason, which is in Fermi liquids. So in Fermi liquids, it's known that when the interactions are strong, so when the Landau parameters becomes bigger than a certain critical number, shear collective modes appear. And funny enough, the elasticity, so the rigidity of the system comes totally from quantum. So the rigidity of the system is just given by the fact that these electrons, they obey Pauli exclusion, and Pauli exclusion is creating basically some kind of rigidity between these electrons in this electron fluid. So this is kind of similar, and I think it's very interesting. There was recently a paper describing all of this. Now, the next question that I want to address here is if holography can help us in understanding this kind of phases of matter. Maybe it's a good point if any of you have any questions about what I said so far, go ahead. Okay, good. So let me continue. So can holography help us? So first of all, I have to give at least one little slide about what is holography, especially given that maybe the audience is not so familiar with it. So holography is nothing too fancy. It's just basically another example of duality in physics. And it's nothing else than the idea that, you know, a certain system can be described in two different ways that we call dual. And for a certain reason, we are lucky enough that one side of this duality is what we want to understand. So for example, the typical, let's say, buzzword that appear are quark-gluon plasma, strange metals, etc., etc. Now, on the other side of the duality is basically described, at least in some limits, by some classical gravity. And this is a good news because classical gravity is much simpler than this kind of system, and we can compute things. So the only idea that you have to take home is that we have this kind of framework where we can compute things from the gravity side and trying to answer questions in systems where other kind of methods are failing or, let's say, are outside the regime of validity. Now, this was the relations between, let's say, gravity and hydrodynamics lies entirely, almost entirely in the physics of black holes. And in the fact that the dynamics of the black hole horizon looks very, very, very similar to basically fluid dynamics, in the sense that basically the physical concept that everything is falling inside the horizon is not so different from dissipations. And the dynamics of basically the perturbation of the black holes are nothing else than, let's say, a mirror or what happens in the fluid if you throw, let's say, a stone. And this, of course, has been formalized in a much more concrete way. And I suggest those of you who are interested to look at this paper where basically they put the basis of these relations between hydrodynamics and gravity. And this, of course, is now used in a lot of different contexts and is basically one of the most important results. The fact that basically the black hole physics is dual in some sense and you reproduce what we know from relativistic hydrodynamics, and therefore it's a good opportunity and a good playground to study basically transport and etc. And all this kind of object that we were discussing before. Now, the most famous result from holography is certainly the bound on the viscosity, and that's where I want to start. So what is this bound? Well, this bound is the observation that it was basically obtained computing the response, the transverse response in black holes using this ADS-CFT correspondence, that the ratio between the viscosity and the entropy of any system in nature should be bounded below by universal value. And basically, the fact that this bound exists is intimately connected to quantum mechanics and to the idea that there is a minimum relaxation time, which comes because of the Heisenberg indetermination. Now, here you can see a plot where some material or some liquids are appear. So here you can see actually the bound. So this bound is this 1/4 pi, which we call KSS bound by the name of the authors. And then you can see basically water. Water is around 30 times higher. Then you see helium, ultra cold Fermi gas, and then you see quark-gluon plasma, and you get closer and closer and closer. So the idea is that basically the closer you go to this bound, the more strongly coupled is the system, just because the viscosity relates to the mean free path. So in very strongly coupled system, we expect the mean free path to be very small and therefore the viscosity to be very small. But what I want to focus today is basically another aspect of this thing, which at the beginning, at least for me, coming from, let's say, black hole physics, was not so clear. And the first question that I want to ask is basically, why the hell there is a minimum here, and what is the reason of this minimum? So the reason of this minimum is basically the dynamical crossover between the dynamics of liquids and the dynamics of gas, which is very different at microscopic level. So in a liquids, as we were discussing, you have the molecules that oscillate around their position, and you have the diffusive chunks that basically rearrange the liquid. Okay, in the liquid sector, basically the viscosity decreases with time, and the diffusivity, so the shear diffusion, is actually inverse proportional to this relaxation time that we were discussing before, which is nothing else than the time of these jumps. Now, if you keep increasing temperature, basically the system will become free, if you like, and the system will become just a free gas of particle, and where ballistic motion applies, and if you like, kinetic theory applies. And then the motion here is just basically a billiard, right? So you have all the particles that scatter around, and where the viscosities in this system come from? Well, the viscosity here comes from the collision, and it can be written down using kinetic theory in this simple way. Well, L is basically the mean free path. And in this case, you can actually see that the viscosity is proportional to this diffusion constant, and it grows with temperature, just because from simple argument of kinetic theory. So putting these two regimes together, you discover that the middle, that we will call the dynamical crossover, the systems have a minimum. So the viscosity in function of temperature have a minimum, and that's exactly what you see in all the systems here. Okay, so this is exactly the temperature of transition. And you can see exactly here that all more or less is set at 0 because these are the units. Now, recently, again, some of my collaborators proposed a different universal bound which applies on the kinematic viscosity. And is written in terms of fundamental constants like h bar, the mass of the electron, and the atomic mass of the liquid that you're considering. And what they find out is basically that all the kinematic viscosities of mostly at least 50 different liquids at the minimum, so exactly at this dynamical crossover, can be derived with this simple formula, which agrees very well with the experimental value, which is more or less this experimental value with basically a prefactor that is order 1, so it's ranging between 0, 5, and 2. And you can see the two important things. So the first thing is that there is a very simple formula that can basically tells you very well what is the value of the viscosity at the minimum. And the second interesting thing is that if you see this plot, you see that basically, at least at the minimum, all the materials are more or less staying at the same position. Now, one important thing is what is the kinematic viscosity compared to the viscosity we were talking before? Well, the kinematic viscosity is nothing else than the diffusion constant of momentum. Why eta over s that we were considering here is not exactly the diffusion of momentum, but is eta over st, which is the diffusion of momentum, okay? So now, taking this kind of result, it appears immediately interesting to us to see what happened if we consider some more exotic fluids, and what happened especially if we consider the kinematic viscosity of quark-gluon plasma, or if you want the diffusion constant of quark-gluon plasma. So we start, let's say, digging in the QCD papers and finding out the various values. And there was immediately one thing which I think it's important to notice, that, you know, in a lot of places you see that the quark-gluon plasma is almost a perfect fluid, right? So this is the slogan that you will see reading everywhere. And therefore you will expect that the viscosity of the system is actually very, very, very low. Well, actually the shear viscosity of quark-gluon plasma is huge. So you can see here is 10 to the 11 Pascal times seconds, which is at least comparable to liquids at the glass transition. So it's much, much more viscous than, let's say, normal water. But the point is that its density is also huge compared to standard liquids. In a way, and this is the magic, that if you take actually the kinematic viscosity, which is the ratio between the shear viscosity and the mass density, the value that you get is again of the same type. So this value can be derived again in several ways, and I suggest you to check the paper that is out in archive. And is also, the funny thing is that it's also consistent with basically the existence of this Planckian relaxation time. So this is kind of surprising because it looks like that even if you plot basically the eta over S ratio, it looks like the minima of these systems are basically living in a very different, let's say, order of magnitudes. But then if you consider basically the kinematic viscosity, there are two things which are very interesting. The first thing is that you can give a very simple formula that can predict basically for you all the values of this minima. And the funny thing is that quark-gluon plasma doesn't look so exotic in the sense that the value at the minimum is comparable to all the other liquids. So this we found very, very surprising and quite interesting. Now, so these are basically the consequences, okay? So the consequence is exactly what I told you so far. And we found, you know, very, very surprising that the viscosity is almost 16 order of magnitude larger than liquids, but because of the density is so huge, the similarity in the kinematic viscosity is very striking. Now, one thing that, one point that it has to be, let's say, emphasized here is that this result supports somehow the idea that the universal quantity it's more related to the diffusivity of momentum rather than eta over S. So the point is that eta over S is a very well-defined concept in relativistic fluids, but it's not so, let's say, easy to understand the appearance of eta over S in a fluid which is non-relativistic. While the diffusion constant of momentum is a quantity which is defined universally, independently of the system that you are considering. And this is somehow also spelled out in this paper, in this famous paper by Arnold in Nature. So now I want to give you another example of this liquids and solids story and introduce you a bit to what we are doing and what are the hot topics in viscoelastic holography in the last 2-3 years. So I will spend a lot of slides, maybe even too much slides, about the motivations, because I think that this is the first important thing that I want to communicate to you rather than specific details or results. So before I go there, is there any questions about the viscosity or anything else? Okay, great. So viscoelastic holography. So what is the idea? So the idea, let's go back to the idea of solids. So what is the solid? So the best way to understand it is that it's a system that breaks translation spontaneously, right? And I like so much this picture to explain basically the spontaneous breaking of translation, because you can see that your system is basically completely invariant under certain symmetries, but then the state is basically breaking this kind of symmetry. And this is, amazingly enough, the reason why the stones are rigid. And the idea from a more, let's say, mathematical perspective is that there is some kind of operator that gets an expectation value, and this expectation value is coordinate dependent or space-time dependent in a way that translations are broken. So the easiest example that you can think about it is just an operator that gets an expectation value which is proportional to the coordinate itself. So of course, the theory of solids can be embedded in the modern formulation of effective field theory. And I suggest you to look at this paper. So the idea is that we can classify all the phases of matter looking at the symmetry breaking pattern of the Poincaré group. So the idea is that our work in the UV fundamentally is, of course, Poincaré invariant. But then when we go to low energy, to the phases of matter and to the low energy ground states, so this symmetry is broken. And depending how this symmetry is broken, you can classify all type of different phases, and you can deduce just with simple effective field theory arguments, which are the excitations there, etc., etc. So this is very powerful. Now, what is the idea, at least the first idea that people had in holography? Well, the first idea was like kind of brute force idea, and was like, well, let's try to search for, let's say, solution of the gravitational equations which are inhomogeneous. So you can put inside some fields, which is x-dependent, that mimics the lattice in your system, and basically the game is done, right? Because this system now will be not homogeneous, translation will be broken, etc., etc. And here you can see some of these cases. You see these are very nice. The problem of these kind of setups is that they're very complicated, because you are trying to solve Einstein equations, which are highly nonlinear, in presence of matter and in presence of backgrounds which are not homogeneous. So these usually are boiled down to solving quite hardcore PDEs. And if you're not good enough with numerics, you don't go so far. That's the reason why basically from this kind of model, we didn't learn a lot in terms of transport, excitation, and quasi-normal mode, just because the computation were so hard that didn't get there. So now the idea, which came out recently, was let's try to make, let's say, a toy model, which we can like manage better and still break translations. So the idea is the following. The idea is exploit global symmetries in the bulk. So here I give you two examples because are the most famous, let's say, models that I will call the axion-like models and the Q-lattice. So the idea is that if you take a field which is linear in the coordinate, but your actions enjoy shift symmetries, and this shift symmetry is actually the typical symmetry of Goldstone boson, then it's clear that the stress tensor that this kind of field will give will be completely homogeneous, because it will be basically always derivative in this field, okay? And therefore, even if these fields break translations, because clearly this setup break translation in X going to X plus a vector, but the geometry that you have, it's homogeneous. And that's why these kind of models are called usually homogeneous model with broken translations. And you can of course perform exactly the same trick by using an exponential, but in this case, not using a shift symmetry, but a global U1. So if you have a field of this kind, and then everything depends only on the absolute value of these fields, of course, the same game applies. So how you should think of these things? You should, of course, forget about any problem of quantum gravity or consistency of these global symmetries. And you can think about this global symmetry and some kind of emergent IR symmetries. And you have to think about these models as toy model for holographic solids. Now, the first immediate question is, do they work? What do we learn from them? And still, let's say, how far can they go? And so, of course, the first sanity check that you have to see in this system is that they behave like solids. And that's exactly what you get. So here you can compute basically the quasi-normal mode, which are the excitation of the system. So for condensed matter people, this would be just the poles of your green functions. And you can do that in basically using linear response. So the idea in holography is that you have your background, so your black holes or gravitational background, and you are just perturbing it. So let's imagine you throw this black hole gravitational waves. Now your black hole will start, let's say, deforming, and the deformations of this object are nothing else than the excitations of the dual field theory. And this is exactly what you get. So very differently from other models like Einstein gravity, etc., you see some nice propagating phonons. And the nice thing is that actually the speed of this phonon can be computed explicitly numerically, and it can be matched exactly to the formula that we know from Landau, where basically the speed is given by the rigidity of the system. So till here, everything is okay, everything is very nice. But then we have to go farther. And so the first thing that I want to tell you is why we are doing this. And I will try to give you a bunch of answers. Some are more theoretical, some are more experimental, but all goes into the same direction. So as I was trying to tell you before, holography has been very successful in describing Stokely coupled fluid. And of course, the first result that I mentioned is the KSS bound, but it's not the only one. Actually, holography allow to discover new hydrodynamic coefficients, and now there is an active, let's say, field of research that is discussing the convergence of hydrodynamics as a perturbative series, etc., etc. So we have plenty of results, and it's very easy to do basically hydrodynamics with holography because everything comes just from basically perturbing your gravitational background. So on the contrary, if you think how you do holography, how you do hydrodynamic usually is the following, right? You start from some conservation equation, which are well defined. So there you don't have any problem. But then you have to add constitutive relations, right? So you imagine you have your stress tensor and you have to start to write down all the possible terms allowed by symmetries. And the big problem there is that, first of all, the number of terms that appear there grows very fast. And the second problem is that if you start breaking symmetries, so for example, you start breaking translation, you start breaking, I don't know, parity, you put a magnetic field, etc., the number of terms becomes very complicated, and it's very, very, very easy to forget one. And this is what happened more than once. Now in holography, if you do your computation correctly, you cannot forget anything because everything just boils down from the equation that you're running. So the idea is to extend basically the success of holography from the fluids to something which looks like more like a solid. Now, why this is interesting also is the following. So the theory of elasticity itself can be written in a standard effective field theory language quite easily. Okay, so this is, for example, an old paper that discussed how to do theory of solids, just looking at phonons as Goldstone bosons and writing down an effective field theory which preserves the symmetry of these Goldstone bosons. Now, the story for dissipative hydrodynamics is very different. And why it's very different? Because the fact that hydrodynamics is dissipative by nature clash immediately with the requirement of effective field theory. So if you want to write an effective field theory, you want to start from some kind of action, and that action better be unitary. And unitary is basically going exactly in contrast with dissipations. So usually what people were doing is exactly what I was discussing before. We start from some conservation equation, we add constitutive relations, and we run the machine. So we do this kind of perturbative expansion in gradients, in derivatives, and we start considering the physics. Only lately, they basically discover how to write hydrodynamics from, let's say, an action, and there is a lot of activity and a lot of results coming out. Now, the question is, what happens if you start to putting them together as in a viscoelasticity? And in viscoelasticity, we are again left to basically a lot of phenomenological models just because of the difficulties in writing from first principle the viscoelastic, let's say, system. Holography in this case can be again very helpful because both ingredients come naturally. The dissipations come just from the fact that you have a black hole, and the theory of elasticity comes because you are putting inside this matter that breaks translations. Now, another very interesting topic is the spontaneous symmetry breaking itself. So this is a theoretical question, and you can imagine that this is a very understood topic, but this is true only under certain conditions. So under certain conditions, and especially basically the fact that the symmetries are global continuous symmetries and Poincare invariance, everything is under control. But when you start actually breaking these assumptions, for example, neglecting Poincare invariance or considering space-time symmetries or considering dissipative system, a lot of surprise come out. And I will show you in a while one of these surprises that at least to me was quite shocking, the existence of diffusive Goldstone bosons. Now, answer number 4 is that we talk a lot about viscosity and elasticity and, for example, the eta-Varese bound, etc., but in general and in various material, of course, viscosity and elasticity are not frequency independent quantities. So the viscosity, for example, depends on the shear rate, and it depends in a very non-trivial way. So there is a full nonlinear regime to explore, and these nonlinear regimes is important because it can make a huge difference between a material. So for example, you can distinguish, let's say, rubber from a metal just in a way that the nonlinear response, the nonlinear elastic response behaves. Now, from a more holography point of view, well, these models have received a lot of success. So you can see here the citations. So the number of work related to this model is actually very, very high, but it's kind of disappointing that still we don't know what they really are. So here I just collect for you a bunch of terms which are associated usually to these kind of systems, and you can see that it's completely a chaos. So one question is that I think it's let's say a duty of any people working in this field is to understand what are these models before applying to something, and maybe they can be useful for something, maybe not, but we have the duty of understanding what they are at least. Now, from a more phenomenological perspective, the interest comes from basically the usual suspect, which are basically ITC superconductor and strange metals. So these are systems with a very exotic phase diagram and a lot of phases which are not understood. So there is this exotic superconductivity here, which is not obeying BCS theory. There is now here another place where basically the normal phase is a metal, but with very weird properties. And the important things to notice here is that there is a large portion of the phase diagram which contain phases where translations are spontaneously broken. So some are called, for example, nematic phases, some charge density wave phase. And you can see that basically there is a structure that forms spontaneously that wants to break translations. Now, a question that is around in condensed matter since probably 20 years is what is the role of these charge density waves and these translations breaking in the onset of superconductivity and in the weird, let's say, properties that we see in these metals. And this is somehow connected to the idea of how phonons behave in a quantum critical matter. So a lot of effort has been dedicated to basically electron transport and especially electric conductivity. But what is the role of phonons? So there is a recent paper by Arnold and collaborators where actually they claim that the strange features that can be experimentally seen in the optical conductivities of these strange metals can be understood exactly from this structure that forms spontaneously and break translations. So in this case, it's important to have some kind of model that can back up this intuition. And finally, and this is more or less where we started with holography, holography is certainly something like an effective field theory, so something that has power in the low IR. So we are talking about universality classes. We cannot, of course, talk about a specific material. And when we talk about universality classes, the first thing that comes to our mind are universal properties. And by universal properties, I mean universal bounds or universal scaling and why they're there. And it turns out, so there is a lot of discussions about these things. And very recently, some of these universal bounds are actually claimed to be experimentally observed in insulator and in its transport especially. And holography is certainly a good platform where we can try to understand and motivate these bounds. Now let me go to the questions that I want to show you today, which is basically the last part of my talk. So of course, we have to understand who are this kind of model. What are this model describing? And this is a fundamental question if we want to apply this, let's say, to cuprates, strange metals, or whatever system you have in mind. Now, I will focus on hydrodynamics, and let me tell you just in a very brief context what I mean by hydrodynamics. So by hydrodynamics, I don't mean what people mean by fluid dynamics. I just mean basically the effective description of a system at low frequency and low momentum. So basically hydrodynamics in this, let's say, notion is just the physics of slow processes and long distance. So you can imagine you have a system, for example, this bunch of surfers in the oceans, and this system has a characteristic length scale, which, for example, here is A. So in a real lattice, in a real solid, this could be the lattice spacing. And hydrodynamics is the theory that describes this kind of system at scales much larger than this, okay? So what do we see in these models when we go to hydrodynamics? So I told you what we see in the transverse spectrum, and everything was very nice. We see phonons and everything collides together in a very nice description. But then when we go to the longitudinal sector, we see something pretty strange. And what is something pretty strange? Well, we see a longitudinal sound, which is again expected from just symmetry breaking quarter, but then we see a diffusive mode. Okay, you can see here there is a diffusive mode that people label crystal diffusions. And the question is, what is this mode? Where it comes from? So what is the physics of this mode? Now, before going on, I have to tell you very briefly what we know or what we knew about this longitudinal diffusive mode. So surprisingly enough, this longitudinal diffusive mode does not come from the breaking of translations, but it comes from the breaking of this global internal symmetry that we were basically throwing there to make our toy model. So if you set a scalar like this to be linear in the coordinate, not only you break the translations in the space-time, but you break also the internal translations, the internal shift in the fields. And the funny thing is that this diffusive mode, and it was proven in this paper by Donos and collaborator, is actually the Goldstone boson, which is associated to the spontaneous symmetry breaking of this symmetry. And the funny thing, which I found very surprising, is that it's diffusive. So this is a diffusive Goldstone boson. And the first thing that you have to ask yourself is, what the heck is a diffusive Goldstone boson and why is appearing there? So other considerations which are important is that in this system, translations are not broken to a discrete subgroup, and this system are not periodic at all, because as I was saying, basically the scalars is linearly proportional to the coordinate. And these systems actually are rotational invariant and also scale invariant, which is something very strange for normal crystals. And there are also some other funny features. For example, the fact that most of the systems are actually metastable. So then I start thinking, okay, how can I make sense? So here there are two options. So one option that you can take is, well, you are putting some garbage global symmetry in the bulk. That global symmetry has completely no sense, and you are getting a mode. Forget about that mode. There's no physics there. Another attitude, a bit more constructive, is, okay, I have this model. Can I make sense of this thing? And this is what I try to do. And this is where I ended up. So I ended up in the physics of aperiodic crystals, which are very funny objects. And so what are aperiodic crystals? Where basically the problem is the following. So imagine you have basically to buy the tiles for your floor of the kitchen. And of course you can be kind of minimal and saying, well, okay, I will do it in a periodic way and just some boring squares like this. Okay, so this is the equivalent of aperiodic crystals. Or you can be more eccentric and you can say, well, I want to actually do it in a funny way, which is not periodic, but still I can, you see, I can tessellate the plane. And so this structure, they have long range order because you can see they have a order, but there's no periodicity at all. So they are somehow in the middle between boring periodic crystals and an amorphous system like a glass where the system is completely disordered. And they were studied a lot by Penrose. So you can find a lot about these in Penrose tilings. And so basically these are systems which are not periodic. And one of the typical example of this system is an incommensurate charge density wave. So what is that? So a charge density wave is exactly this kind of spontaneous structure that I was telling you in the context of cuprates and strange metals, where basically the charge of the systems wants to organize itself in some kind of periodic structure. But you have always to remember that basically there is always an underlying ionic lattice. And then you have various options. The two can be commensurate, so basically the spacing, the wave vector of the two, the periodicity can be basically proportional or be the same, but it can also be that the things are completely incommensurate. And in this case, the full structure that you get, the full system, is clearly not periodic. And now you can ask yourself, well, okay, how we understand this? And it turns out that there is a very nice mathematical description of not periodic, aperiodic, let's say, crystals, which is called superspace description. So let me first read for you the statement. So the statement is that any aperiodic crystals is basically can be seen as a periodic crystal in a higher dimension, cut at an irrational angle. So what this means, let's go through the example, which is very suggestive. So here you have to think that your crystal is one-dimensional, and we're trying to embed it in a two-dimensional structure. So the two-dimensional structure that I choose here is a periodic square lattice with a certain, let's say, lattice spacing. And then what this kind of line is the line of my real crystal, or the one-dimensional crystal, which cuts this kind of periodic higher dimensional structure at a certain angle. Here I choose, for simplicity, 45 degrees. Now, what you have to do is that you start from, let's say, the higher dimensional picture, and you collapse or you project the lattice point in the real space-time of your one-dimensional crystal. And you can see that if the angle is rational, like 45 degrees, the structure that you get on the crystal is still periodic. It has, of course, a different periodicity because of the angle, basically it's just the cosine of this angle, but it's still periodic. But now, let's try to cut this higher dimensional structure with an angle which is irrational. Okay, you take some square root of whatever, and you do that, and then we do exactly the same game. So we project, and you can see that now the structure that you get here is not periodic. So if you identify the longer distance with L and the smallest distance with S, you can see that this actually series is exactly like this. And it's not periodic because you can see here there are actually 3 long, let's say, distances, and here only 2. So this is not periodic. So this is very suggestive because somehow it gives us a way of describing these non-periodic crystals, which was actually very successful in the past. And now we go to the actual physics, and you can ask yourself, well, what is the difference between basically an aperiodic crystal and a periodic crystal? Is there something different, or it's just, you know, whatever, the microscopic lattice structure is different? And the answer is that there is something different. So aperiodic crystals, they have an additional Goldstone mode, which is called PHASON. And this PHASON, interestingly enough, has a diffusive dispersion relation. So here you can see, for example, a plot, an experiment where they probe these things. And where this dispersion with this Goldstone boson appear, well, this Goldstone boson appear, it can be understood somehow from this picture. So from this picture, you can see that in your real crystal, there are displacements which are in the internal space, so in the real space, sorry, here I call it external space, in the external space, so in the real space-time where the crystal lives, but there are also displacement that goes in this kind of internal directions. Okay, so you can convince yourself pretty easily that this kind of projection, of course, is invariant if you shift this object here, and this is exactly where this kind of object comes from, so this new Goldstone boson. Now, interesting enough, I haven't found anywhere, let's say, an effective field theory description of why this mode is actually quadratic and is not linear. And it seems to me that this problem is quite similar to what happened in graphene with flexural phonons. So with phonons which are actually perpendicular to the two-dimensional layer of graphene. And there I found an interesting paper of last year that describes quite simply why this mode is quadratic. And I think something of that kind can apply also here. So the idea is again, the same idea of non-relativistic, let's say, effective field theory for Goldstone boson, where basically you are breaking different symmetries, but the symmetries do not commute between themselves. So the generator that you are broken basically are not independent, and therefore you get less Goldstone boson, and Goldstone boson that goes with higher power of momentum. And this is exactly how it was proven, for example, for flexural phonons. Now, this is again a bit how you should understand these this kind of phasons. So there are the phonons, which are basically the translations of the atoms, and then there is these phasons, which are the rearrangement of the atom. So are basically the rearrangements along this cut, this irrational cut. And this gives rise to basically what sometimes is called like solid diffusion. And obviously, this solid diffusion needs basically temperature. So if you set the temperature to 0, you would not see any of this phason. And that's the reason why, for example, in the effective field theory of Nicolis and friends that I mentioned before, you won't see anything like that. And here there is an analogy with the model that we are considering, which is exactly the following. So here you can consider that basically we have a solution, a scalar, which is linear in the coordinate. And of course, when you assume this to be the ground state, you are breaking two different kinds of symmetries. One is the space-time direction symmetry, so the shift in the real direction, so what we call usually space-time translations, and this gives rise to phonons. But there is also an internal direction that you can picture somehow like transverse to the real directions, which is like the field direction. And here you're also breaking a symmetry. You're breaking this global symmetry. And these kind of modes here are related to this diffusive phason that I was discussing. Now, this is a bit a more technical slide, which goes back to diffusive Goldstone. And I think it's very interesting. I'm already almost out of time, so I will not go into the details, but I forward you to this nice paper, which to my knowledge are the only paper that discuss the existence of diffusive Goldstone. And the important point that you have to take home with yourself is that diffusive Goldstone can exist only in dissipative systems. And what these people do, you can check in the paper, they do this very simple exercise. Consider a field theory where you have some spontaneous symmetry breaking, like let's say the Mexican hat, the typical Mexican hat, but consider this as an open system. So couple this field theory to a buff, to an external buff, like we do typically in Langevin equation or in Brownian motion. And try to see how dissipation into this buff, which is kind of thermal, affects the dispersion relations of the Goldstone boson that comes because of the spontaneous symmetry break. And what they find out is that these Goldstone bosons are not propagating anymore, but they become diffusive because of this dissipation. And in this other paper, more recent, there is basically a same kind of treatment, but using coset techniques. So these are more advanced techniques, very used in the context of Goldstone boson, and basically the conclusions are more or less the same. Now, of course, we're talking a lot about this diffusive Goldstone boson, and the question is, are they real? And the answer is yes. And very surprisingly, one of the places where you see diffusive Goldstone boson are actually flocks of birds. So I guess all of you have seen, you know, in spring, all the flocks of birds migrating and having these funny shapes and very, very artistic thing, right? And it turns out that these kind of flocks can be described by another dynamic theory. And in this dynamic theory, it appears exactly one diffusive Goldstone, exactly like I was discussing. Other places where this happens is active matter and open systems. So of course you need some kind of dissipation somewhere. Now, so we go back to what we were saying. So we had a long trip up and down, jumping from different topics, and we learn at least something. So now if, you know, our child come back to us and ask, okay, daddy, what is the difference between a solid and liquids? Or can you tell me a story about them? Well, we are kind of happy. So, you know, we are fine. But then our child come back and with a glass of water, and he asked us like, okay, and then what is this? Is this a solid or is this a fluid, the glass? And here we go back to another big topic, and I want just to flash some results because I got very interested in this topic recently, which is the following. So why glasses are exotic and what are glasses? Well, glasses are exotic at least for 3 different reasons. So the first reason why they are exotic is that basically they have what is called the boson peak. So the boson peak means that the Debye theory for phonons fails. So you probably know very well the Debye theory, right? Which is the standard condensed matter theory to describe the specific heat, the thermal transport, and the density of states of phonons and vibrations in solid. Well, in glasses, this fails brutally. And the way it fails is that the density of state, accordingly to Debye theory, should go like the frequency square. But here, if you plot actually the Raman intensity from experiment normalized by this Debye theory, it should be a line. You will see a huge peak. And this huge peak usually is more or less around terahertz scale and is universal in all classes. So this means that the Debye theory fails. And then, therefore, we have to find out some other, let's say, discussion or some other framework. And this is not surprising, right? Because imagine you have a system which is completely disordered, like a glass. Momentum is definitely not a very well-defined quantum number. And therefore, talking about phonons and as Goldstone boson of momentum, it doesn't make much sense. Now, there is another feature which is discussed a lot, which is the specific heat, right? The specific heat, accordingly to the Debye theory, scales like T to the D, T to the cube, for example, in normal solid. Well, in glasses, you see that at low temperature, there is a linearity behavior, which can be easily observed. And one of the explanations is the so-called existence of these famous 2-level states by Anderson, which is, of course, very successful, but is, on the other point of view, kind of frustrating because nobody ever saw any 2-level state whatsoever. And then there is another, let's say, properties, which is very anomalous, which is the thermal conductivity, which also scale in a very different way. And somehow these kind of anomalous properties of glasses are kind of related to each other. And the only thing that I want to flash to you is that recently we basically study a bit how phonons will behave in glasses or in disorder system, taking a very simple hydrodynamics and effective field theory approach. So what we did is that instead of considering basically the typical green function for just Debye theory that will give us the density of state proportional to omega squared, we add 2 different terms. So one term is basically a diffusive term. So this diffusive term is motivated by several means, and it's also experimentally seen in simulations for glasses. And then we put another term which takes into account the flattening of basically the phonon dispersion relations. And quite surprisingly, with this very simple setup, we were able to basically fit a lot of data of basically glasses found in the past, and to explain very universally why a boson peak appears. So the boson peak, so this peak that you saw here, appears very universally just because of the competition between these propagating terms and this diffusive term. And this is not surprising because it was already known that this peak correlates with what is called the Joffe-Regel crossover, which is exactly the crossover, the frequency at which a particle put in a disordered system stops to propagate and becomes diffusive. And the Joffe-Regel frequency comes exactly from basically compare these terms with these terms. And we saw also some interesting scaling which were observed in simulation. So this is quite funny. I was very surprised because it's a very simple theory. So you can see this paper here that we published last year in PRL. And you can see that despite the simplicity, it universally reproduced a lot of features that were observed and also predicted with other models by using much more complicated setups. And the funny thing is that going back to this idea of diffusion, that is that basically appear in a disorder system. So what you have to understand is basically the following. So if you are in a disorder system and you are some kind of ballistic propagation, you have to understand like disorder is some kind of localized impurity that scatter your ballistic propagation. And at a certain point, if you are too much disorder, of course, the scattering becomes so intense that basically you are not moving anyway, and you are just doing some kind of random walk. And this random walk gives rise to diffusion. And now the question is, okay, we know very well that if you assume ballistic propagation, like in Debye theory or in perfect solids, you get basically that the specific heat goes like T cubed. This is Debye theory. So now our question, which was very basic, is what happens if you include, actually, if you consider something like a diffusive motion? What is a specific heat for these modes? And so maybe not surprisingly, we found that these kind of motions give a contribution to the specific heat, which is linear. And it becomes important, more important, the bigger, basically the more localized the modes become. So basically with this simple model, we can also reproduce the linear anti-specific heat from diffusions. And this is some kind of alternative to two-level state, and it reproduces also results that were found using random matrix. So basically this kind of curved blue that you see here is a random matrix, let's say, descriptions of glasses, which give rise to these very weird, let's say, density of states. And this is our simple model. And you can see that at low frequency, which of course is where this kind of simple model works, we can kind of reproduce very well the behavior, so that the constant behavior and then the square behavior that come from Debye. And I find very, very interesting to understand better the dynamics of spontaneous symmetry breaking and phonons in these kind of systems, which are basically amorphous. And so I want to conclude here my talk by saying that this simple exercise that, you know, our child proposed to us, it's not that simple as it looks like, but for sure it's very interesting, and we can learn a lot about phases of matter, which we thought were very simple to understand. Even solid and liquid, even the standard fundamental questions of the difference between solid and liquid gave us a lot of surprise. And with this, I want to thank everybody for following the talk, and I want to thank once more Joshua and the organizer for keeping these very nice initiatives.
Okay, so if anyone has any questions, just unmute yourself. You can ask them. So we have some time for questions.
Hi, thank you for the really great talk. I just had a question about this diffusive Goldstone mode. So what if I'm understanding you correctly, what you're saying is the appearance of an aperiodic crystal corresponds to this, this diffusive Goldstone mode. Is that correct?
Yeah, so let me tell you, so two fundamental things about this diffusive Goldstone mode. So the first thing that we learn, and I suggest you to have a look at this paper here, which are kind of technical but very suggestive, is that in order to have a Goldstone boson which is diffusive, you need dissipation. So that's the first statement. Now the second statement is that in these aperiodic crystals or quasicrystals, you can find everywhere that basically there is this kind of diffusive Goldstone boson, which is called PHASON, which is experimentally observed. And but to the best of my knowledge, as I said, I couldn't find a nice effective field theory description of why this mode is there. So if you search in the literature, you will find a lot of you know, juggling and mumbling about this comes from the displacement in these things and blah blah blah. But I don't think, at least from my perspective, no satisfactory answer is there. So before, there was basically a suggestion for those of you who are interested in an expert in effective field theory to look at this, because I think it's something interesting. And it's interesting to understand why this mode is diffusive. There should be a simple argument coming from symmetries.
Okay, interesting. I kind of asked that because maybe from my limited experience in helium-3, we have found some evidence of this crystal that appears in the superfluid. And there's a thought that this crystal actually appears because of the softening of a massive mode. And so I was wondering if there was a connection here. So if we can think of crystals as appearing due to softening of a massive mode, aperiodic crystals appear due to this appearance of a diffusive Goldstone boson. Yeah, I was wondering if there was a connection there. I don't know if you can speak more about that.
Yeah, I'm not so sure what I can say about it. I mean, I'm not an expert in helium-4 or superfluid, but it's definitely interesting. So if you want to send me maybe the link or something, I'm happy to have a look and see.
Okay, thank you.
So I also have a question about this. So basically, so you're saying that first, so there are these two observations. One of them is that it's related to this like quasicrystal, and second that you need dissipation. So is it possible then to interpret like that this dissipation, like from this picture which we can see now, that this dissipation kind of comes from all these external degrees of freedom of this two-dimensional like regular solid, or so how?
Yeah, so the idea that I have is more like maybe can be understood better in this picture. So you can imagine that basically the movement of the atoms in the extra dimension, in this kind of extra dimension that you were mentioning here, in the crystal itself, as basically rearrangements of these atom positions. And these rearrangements are kind of thermally activated. So you need some energy to actually rearrange these things.
And from the point of view of this 1D system, it acts as like dissipation, right? Because you can lose energy to kind of external bath or exchange it.
And this is exactly the point of this paper. So what these papers are doing are exactly studying basically the standard effective field theory for let's say spontaneous symmetry breaking in context of dissipation. So in open systems, in basically what they're considering, if I remember well, are Brownian motion, Langevin systems, Lindblad kind of systems, and they do also some kind of Keldy-Schwinger formalism. And there they claim that if you basically consider the typical Watanabe-Browner matrix, etc., you will find out that there is a symmetric part that comes from dissipations, and that basically when you solve this equation, you can classify accordingly to the usual rank and stuff like that, basically the type of Goldstone boson. And you can find out that at low momentum, there are Goldstone boson that appears, and they appear like diffusive. And to me, I couldn't find any other reference that actually mention any kind of diffusive Goldstone boson. And it's very interesting because then you can ask yourself a lot of questions about Goldstone boson. You can start asking, for example, what about the Mermin-Wagner theorem for diffusive Goldstone boson, or how this affects, you know, the physics in general. And but yeah, one statement that I'm totally sure is that you need some kind of dissipation. That's necessary. And this is related to the fact that, for example, in this holographic system, we see that this mode is there only if you are at finite temperature.
And so this data for this aperiodic, so you have, exactly. So could you, is it some kind of experiment, or how could you tell more about
this?
So
these are experimental data. So this is basically what they are doing is they are measuring the relaxation time of these modes that appear. And you can see here, so the relaxation time is basically taken to be this kind of, the inverse of this object here. And what they are claiming is that this data, with a bit of fantasy, they follow a line with Q square, which tells you that basically these things is exactly basically diffusive. And it's the fact that it's imaginary is just because this is not the position of the peak, but it's basically the width of the peak. So what they observe is that there is a peak in the experiment with a certain width, and this width goes exactly like quadratical with the momentum.
And is it like some kind of temperature dependent, or how
well, so this is the only kind of experiment that I found. I haven't found any study of, for example, how this kind of behavior change with temperature. So this is probably due to my, you know, my difficulty in finding reference in this field. But to the best of my knowledge, I haven't found anything. So it would be, of course, interesting, as you are suggesting, like, you know, changing the temperature and see how the dispersion relation is changing. for example, decreasing the temperature, this behavior should disappear somehow. So this the diffusion constant should go to 0. So basically this line should go slowly down to 0, decreasing the temperature if this is true.
Mm-hmm. And this is in some kind of incommensurate solid, right? Or
yes,
like
exactly.
or density.
So if you're interested, I can send you after
something like that, right?
Yeah, I can send you after the reference, and you can. I didn't write it here in the slides.
Okay.
I can send to you. Yeah.
Mm-hmm. Okay. Thank you.
Welcome.
Okay. Any other questions? So I had one quick question. So, what is when earlier in the talk you talked about the momentum gap, right? So could you go over quickly again how the formation of the momentum gap is connected to, say, the interplay of whether or not it's a solid or a liquid?
Yeah. So the fact, yeah, the idea is the following. So the idea is that the difference between a solid and a liquid is basically the fact that a solid has transverse propagating waves, shear waves, and the liquid has not. So now the point is that, as I show you, it was long known that this is not a true statement if you go at high frequency, but people were thinking that this is a true statement when you go to low frequency. But now I show you some experiment, and there are actually others that appear recently about thermal transport that seems to indicate that this is not true even at low frequency. So now the idea is, how can you understand, let's say theoretically, the appearance in liquids of transverse propagating wave? And the catch is that this can happen only if you watch at very large momentum, so at very short distance. And here, basically, there is this equation that I didn't derive, but there is a way to derive this equation actually in several ways. And this is an equation that looks very simple, and it appears in a lot of different situations. And the funny thing is that basically this kind of equation provide for you a simple explanation of why a system should behave like a liquid at small momenta and as a solid at large momenta. And funny enough, when we start digging into this equation in this review that you find in physics reports, we actually found that this kind of behavior appear in a lot of different systems. So for example, I think I have some backup slides where I can show you some of the system where this happens. Okay, so this is the way to deriving, actually how Maxwell and Frenkel derive it. So they just took Navier-Stokes equation and they did a very phenomenologically, let's say, I don't know, trick to get this kind of equation. But the funny thing is that, let me see if I have, yes. So first of all, this kind of K-gap is observed in plasmas. And here is something that, for example, you see in some experiments. So we talk about this. And another place where this is actually discussed is in electromagnetic waves in a medium. And the point is that usually in electromagnetic wave in the medium, we solve the equation in terms of momentum. And we talk about penetration length and things like that. Well, actually the penetration length has a lot to do with this K-gap seen in the opposite way. So what you can understand is basically penetration length determines how much a wave can propagate. So you can think about a fluid like a solid where the transverse wave can propagate only a bit. And then it's lost. So that's basically the picture. And it happens actually, for those of you who are interested in, for example, in a system with anomalies, it happens also in chiral magnetic waves. So this is a paper that I took from Lensteiner and Stefanov, and you can really see that they discuss the same kind of dispersion relations appearing in chiral magnetic waves. So we were kind of surprised that you can really find these things everywhere. And this is the other experiment that I was mentioning where they actually found this. So they clearly say that this challenged the dogma of fluid dynamics in the abstract. So yeah, this is a bit the story. But I suggest you to have a look at the review. There we say much more than what I had time to say.
And you said we've seen this in Fermi liquids?
No, I'm not saying that we've seen this in Fermi liquids. What I'm saying is that there is something funny also happening in Fermi liquids, which of course we think they are liquids, but if you go at a strong interaction, so you take the Landau parameter large, if I remember well, you have to take basically F1 to be larger than 6 or something like that. Then what you find, which is what I mentioned here, is you find a regime. Yeah, you can see here. This is the omega tau, and this is F1, the Landau parameter. So if you go at kind of high frequency, but not so much high, and then you crank up the interaction in the Fermi liquid, what you see is that there is a huge region where propagating shear modes appear. And the more you make the interaction strong, the more this kind of propagation goes low frequency. And you can find all the details here. And they also told me that they submitted the paper to Nature with basically the experimental confirmation of these things. So basically you can see shear collective modes in the transverse sector in Fermi liquids, which is kind of analogous to basically what we were saying. So this is a liquid, but it has some kind of rigidity. And here it comes from pole exclusion, so it's completely different setup.
Okay.
Joshua?
Yes.
This is Kevin Vidal. Just this picture you just showed on the value of the F1S and all that before you get into this shear mode. Chris Pethick and I, in the early 80s, had this calculation that we did in the context of helium-3 and showed that you should have a shear wave when F1S was larger than some number, I get 6 or whatever it was. But the thing is, they actually measured it too. So there is this viscoelastic model that we showed what comes out of the Fermi liquid theory as you go up to this very large values of both F0S and F1S pressure. Low pressure, it doesn't propagate, but high pressure, you can see it. You can do the calculation exactly for in the context of the Fermi liquid. So this is
I see.
not new.
Okay, then I wasn't aware. For me, this was the first time I saw that, but yeah.
They
so,
probably didn't reference it because it's an ancient history being back in the 80s. So,
yeah, it might be.
It's been there. And then we also did a calculation in the cold atom systems where you have a gas close to a superconducting transition, and the superconducting fluctuations give rise to stronger interactions, which cause a change for the gas actually to become like a viscoelastic system.
This is very interesting because for me, it's quite counterintuitive, the fact that the stronger the interaction and you produce something propagating, because I was believing that, the stronger the interaction, you destroy anything that propagates. So it's something funny here.
Well, it depends on the sign of it. If it's a large and positive, you have this strong interaction that's causing it to have a very stiff response, and it moves itself into this kind of funny phase. It's with all the understanding of what fluids were versus what solids were. If you talk to people who are old-time hydrodynamic people, they don't understand it at all.
I see.
So
that's very interesting. Yeah. Would you mind to send me that reference?
Yeah, no, not a problem.
Thank you.
Yeah, actually send me that too.
You have it. It's
Okay.
the Pethick and it's Vidal and Pethick.
Oh, okay.
Journal
I think I do.
of Physics, 1982.
Okay, I think I do have that one. Okay.
Matt should know it also. I mean, he has it.
Okay. Okay. Any other questions? Okay, so maybe let's thank Matteo one more time.
Thank you so much.
Okay.
So I see you next talk.
Yes. Bye.